World War II fundamentally transformed military aviation from a supplementary reconnaissance tool into the decisive element of modern warfare. Between 1939 and 1945, aerial combat evolved through rapid technological innovation, tactical adaptation, and strategic implementation on an unprecedented scale. This analysis examines 6 interconnected dimensions of air warfare that define the conflict. First, the technical characteristics and tactical employment of fighter aircraft through comparative analysis of the Supermarine Spitfire and Messerschmitt Bf 109. Second, the development and effectiveness of night fighter operations. Third, the strategic and operational dimensions of the Battle of Britain. Fourth, the strategic bombing campaign against Germany from both operational and strategic perspectives. Fifth, the revolution in naval warfare represented by carrier operations at Coral Sea and Midway. And finally, the Kamikaze phenomenon as a case study in asymmetric aerial warfare under conditions of material inferiority. Our methodology combines technical specifications, operational data, tactical analysis, and strategic assessment. We examine primary source combat reports, engineering documents, and post-war statistical analysis to construct an evidence-based understanding of how air power shaped the war's outcome. The objective is not merely to recount events, but to analyze the systematic factors, technological, tactical, operational, and strategic, that determine success or failure in aerial warfare during this transformative period. Part 1. Fighter Combat Dynamics. 1.1 Engineering Analysis. Spitfire and Bf 109 Design Philosophy. Effective analysis of fighter combat requires understanding the engineering principles underlying aircraft design and their tactical implications. The Supermarine Spitfire originated from Air Ministry Specification F.37/34, calling for a modern 8-gun fighter. Chief designer Reginald Joseph Mitchell synthesized aerodynamic efficiency with operational requirements. The Spitfire Mark I, entering squadron service in August 1938, featured an all-metal monocoque fuselage and the distinctive elliptical wing platform. The wing design merits detailed examination. The elliptical shape provided optimal lift distribution across the span, minimizing induced drag while maximizing lift coefficient. Wing area measured 242 square feet, producing wing loading of approximately 24.9 pounds per square foot at combat weight. This relatively low wing loading translated directly into superior turning performance, a critical advantage in close-range combat. Power plant specifications. The Rolls-Royce Merlin II, a liquid-cooled V12 engine displacing 27 liters, produced 1,030 horsepower at 3,000 revolutions per minute at 16,250 feet. The 2-speed, single-stage supercharger maintained power output at altitude. Maximum speed reached 362 miles per hour at 18,500 feet. Rate of climb measured 2,530 feet per minute at sea level, decreasing with altitude as air density diminished. Armament consisted of 8 Browning .303 caliber machine guns, for per wing, positioned outside the propeller arc. Total ammunition capacity, 2,660 rounds, providing approximately 14 seconds of continuous fire. Muzzle velocity of 2,440 feet per second and rate of fire of 1,200 rounds per minute per gun created a combined theoretical output of 9,600 rounds per minute. However, the .303 caliber projectile, weighing 174 grains, carried limited kinetic energy, requiring multiple hits to inflict critical damage on military aircraft structures. The Messerschmitt Bf 109E represented a contrasting design philosophy. Willy Messerschmitt prioritized production, efficiency, and performance over handling characteristics. The aircraft featured a narrow-track landing gear, retracted outward into the wings, simplifying the undercarriage mechanism, but creating ground handling difficulties. The cantilever low-wing monoplane configuration with leading-edge slats and slotted flaps provided excellent low-speed handling characteristics while maintaining structural simplicity. Technical specifications of the Bf-109E3. The Daimler-Benz DB601AA, an inverted V12 liquid-cooled engine displacing 33.9 liters, produced 1,175 horsepower. Direct fuel injection eliminated carburetor limitations during negative-G maneuvers, providing a significant tactical advantage. Maximum speed, 354 miles per hour at 12,300 feet. Rate of climb, 3,100 feet per minute initially, superior to the Spitfire at low to medium altitudes. Wing area of 174 square feet produced wing loading of 32 pounds per square foot, 28% higher than the Spitfire, resulting in inferior turning radius but superior roll rate due to reduced wing mass. Armament represented a mixed configuration, two 7.92mm MG-17 machine guns mounted in the upper engine cowling with 1,000 rounds per gun, synchronized to fire through the propeller arc, and two 20mm MG-FF cannon in the wings with 60 rounds per gun. The 20mm cannon fired a 134-gram high-explosive projectile at 585 meters per second. Despite lower muzzle velocity than machine guns, the explosive warhead delivered substantially greater destructive effect per hit. The tactical trade-off, greater lethality, but severely limited ammunition capacity, requiring fire discipline and precision. 1.2 Comparative performance analysis under combat conditions. Aircraft performance specifications measured under test conditions provide incomplete understanding of combat effectiveness. Real-world engagements occurred under variable conditions affecting performance parameters. Altitude profoundly influenced relative performance. Below 15,000 feet, the Bf-109E demonstrated superior acceleration and climb rate. The higher power-to-weight ratio, 0.195 horsepower per pound versus 0.165 for the Spitfire, translated into kinetic energy advantages. In practical terms, a Bf-109 pilot could accelerate away from combat situations or climb to advantageous position more rapidly than Spitfire opponents. However, turning combat revealed different characteristics. Turn radius depends on wing loading and lift coefficient. The Spitfire's lower wing loading enabled tighter sustained turns at equivalent speeds. Combat reports consistently document Spitfire pilots successfully defending against Bf-109 attacks through hard-turning maneuvers that Bf-109s could not match without excessive energy loss. The concept of energy management proves critical to understanding fighter combat. Aircraft possess two forms of energy: kinetic energy from velocity and potential energy from altitude. Total energy determines tactical options. A pilot can trade altitude for speed in a dive or speed for altitude in a climb. The Bf-109's superior acceleration and climb rate provided advantages in energy warfare, while the Spitfire's turning ability enabled successful defense when energy states equalized. Roll rate, the speed at which an aircraft rotates around its longitudinal axis, affected combat effectiveness significantly. The Bf-109's slotted flaps and ailerons initially provided superior roll rate, though later Spitfire variants addressed this through aerodynamic modifications. Superior roll rate enabled rapid transition into and out of maneuvers, particularly important for offensive gun solutions and defensive brakes. Engine performance characteristics created tactical asymmetries. The DB601's direct fuel injection maintained function during negative-G maneuvers, while the Merlin's float carburetor temporarily starved of fuel during negative-G loads. causing momentary power loss. Luftwaffe pilots exploited this by pushing into inverted dives when pursued by Spitfires, knowing the RAF aircraft would momentarily lose power. RAF pilots developed the half-roll and dive technique, rolling inverted, then pulling into a dive, maintaining positive G throughout to circumvent this limitation. 1.3 Night Fighter Operations, Technology and Tactics. Night operations represented a distinct domain of aerial warfare, requiring specialized equipment and tactics. The Luftwaffe developed the most sophisticated night fighter force of the war, responding to RAF Bomber Command's nocturnal offensive. The fundamental challenge of night interception, locating and engaging enemy aircraft in darkness across vast airspace volumes. Human visual capacity degrades severely in low-light conditions. Under optimal night conditions, pilots might detect aircraft silhouettes against lighter sky at ranges of 1,000 to 2,000 feet, insufficient for controlled interception. Technology provided the solution. Ground-based radar. Initially, the Freya system, operating at 2.4-meter wavelength, detected bomber formations at ranges exceeding 100 kilometers. Würzburg radar, operating at 53-centimeter wavelength, provided precision tracking for ground-controlled interception. The Himmelbett system divided defended airspace into sectors, each covered by dedicated Würzburg radars tracking both bomber and interceptor, with ground controllers providing verbal guidance to position fighters for visual contact. This system achieved significant success during 1941 to 1942, but possessed limitations. Each Himmelbett zone could control only one interception simultaneously. RAF bomber streams saturated individual zones, overwhelming capacity. The solution: airborne interception radar enabling autonomous target engagement. The Liechtenstein BC radar, introduced operationally in 1942, employed 4 dipole antennas mounted on the aircraft nose. Operating at 490 MHz with 1.4 kilowatts peak power, detection range against bomber-sized targets reached 4,000 meters, with minimum range of 200 meters. The system displayed target position on a cathode ray tube, showing azimuth and elevation relative to the fighter. Operators. Night fighters typically carried a radar operator in addition to the pilot, guided pilots into visual range for weapons employment. Primary German night fighters included modified Messerschmitt Bf 110 twin-engine fighters and purpose-built Junkers Ju-88C variants. Twin-engine aircraft provided necessary range, endurance, and space for radar equipment and operators. Armament typically consisted of upward-firing cannon in a Schrage Music installation, enabling attacks against bombers' undefended ventral surfaces. The British developed complementary systems. Ground-controlled interception relied on chain-home radar for initial detection and dedicated GCI stations for fighter control. Airborne interception Mark IV radar, operating at 1.5-meter wavelength, equipped Bristol Beaufighter and later de Havilland Mosquito night fighters. These aircraft defended British airspace against Luftwaffe night raids and later pursued intruder operations over occupied Europe. The night fighter war evolved into technological competition. RAF introduced window strips of aluminum foil cut to radar wavelength, which created false returns overwhelming German radars. Luftwaffe responded with Naxos passive receivers homing on British H-2S ground mapping radar emissions. British deployed Serrate receivers detecting German radar emissions. This action-reaction cycle continued throughout the war, with each side developing countermeasures to opponent innovations. 1.4 Tactical evolution and combat effectiveness. Fighter tactics evolved continuously through operational experience. Pre-war formations, optimized for visual cohesion, proved catastrophically inadequate under combat conditions. RAF Fighter Command entered the war employing 3 aircraft VIC formations and multi-VIC squadron formations. The VIC placed aircraft in close proximity, approximately 1 wingspan separation, requiring constant attention to avoid collision. This reduced situational awareness and mutual support capability. The rigid formation structure prevented flexible response to threats. Combat experience during the Battle of France and early Battle of Britain demonstrated these deficiencies. Squadron leader J. Johnny Johnson later wrote that the VIC formation was based on the peacetime idea of tidy formations for air displays and not on the hard facts of aerial warfare. Losses mounted as German fighters, employing superior tactical formations, achieved surprise and superior kill ratios. The Luftwaffe employed swarm tactics developed during the Spanish Civil War. The fundamental element consisted of the ROT, 2 aircraft separated laterally by 180 to 270 meters, with the wingman positioned slightly behind and above the leader. This spacing enabled both pilots to scan for threats rather than focus on formation maintenance. The leader conducted navigation and primary engagement, while the wingman provided surveillance and protection. 2 Rotten formed a swarm of 4 aircraft, creating a flexible, mutually supporting formation. The spacing allowed for wide visual coverage and rapid response to threats from any direction. Aircraft could engage independently while maintaining mutual support, or concentrate against single targets as circumstances required. RAF Fighter Command progressively adopted modified versions of German formations. By late 1940, squadrons increasingly employed finger 4 formations for aircraft positioned like fingertips of an outstretched hand when viewed from above. This provided similar advantages to the swarm: visual coverage, flexibility, and mutual support. Combat effectiveness measurements reveal the impact of these tactical evolutions. During July 1940, RAF Fighter Command achieved approximately 1.1 confirmed kills per aircraft lost in combat with Bf 109s. By September 1940, this improved to 1.4:1, reflecting improved tactics, pilot experience, and advantageous defensive positioning. By 1941, with fully implemented finger 4 formations and improved tactical doctrine, ratios approached 2:1 in Fighter Command's favor during defensive operations. Part 2. The Battle of Britain, System versus Force. 2.1 Strategic Context and Force Structure. The Battle of Britain represented the first major campaign conducted entirely through air operations. Following France's capitulation on June 22, 1940, Britain faced potential invasion. German operational planning for Operation Sea Lion, the amphibious invasion, required air superiority as an absolute prerequisite. The Kriegsmarine could not contest Royal Navy superiority without Luftwaffe air cover. Thus, Reichsmarschall Hermann Göring received orders to achieve air superiority over southern England and the Channel. Luftwaffe order of battle for the campaign. Luftflotte II, commanded by General Feldmarschall Albert Kesselring, operated from bases in northeast France, Belgium, and Holland. Luftflotte III, under General Feldmarschall Hugo Spurl, deployed from northwest France. Luftflotte V, commanded by General Oberst Hans-Jürgen Stumpf, operated from Norway and Denmark. Combined strength as of August 10, 1940. Approximately 2,550 serviceable aircraft from total inventory of 3,358 aircraft. Detailed composition: 998 Heinkel He 111, Dornier Du 17, and Junkers Ju, 88 medium bombers, 261 Junkers Ju 87 Stuka bombers, 805 Messerschmitt Bf, 109 E single-engine fighters, 224 Messerschmitt Bf, 110 twin-engine fighters, plus reconnaissance, coastal, and transport aircraft. This represented formidable striking power, concentrated against a geographically limited target area. RAF Fighter Command, commanded by Air Chief Marshal Sir Hugh Dowding, organized defenses into groups corresponding to geographical sectors. Number 11 Group, under Air Vice Marshal Keith Park, defended southeast England, including London, the area of heaviest combat. Number 12 Group, commanded by Air Vice Marshal Trafford Leigh-Mallory, covered the Midlands. Number 10 Group defended southwest England. Number 13 Group covered northern England and Scotland. Fighter strength fluctuated, but averaged approximately 700 operational aircraft from total inventory of 1,000 fighters. Detailed composition emphasized Hurricane and Spitfire single-engine fighters, with Hawker Hurricane constituting approximately 60% of operational aircraft. While Hurricane performance lagged behind Spitfire and Bf 109, it provided stable gun platform with heavy firepower, proving highly effective against bomber formations. Numerical comparison reveals apparent German advantage. However, pure aircraft counts provide incomplete assessment. Fighter Command operated over home territory with intact infrastructure, comprehensive maintenance facilities, and established logistics. Downed pilots could return to service. Damaged aircraft could undergo repair. The Luftwaffe operated at maximum range from forward bases with limited maintenance capacity. Downed pilots became prisoners. Damaged aircraft often could not return across the channel. 2.2 The Integrated Air Defense System. Britain's defensive capability extended far beyond fighter aircraft numbers. Air Chief Marshal Dowding had developed an integrated system combining detection, command and control, and interception, the first comprehensive application of these principles in military aviation. The chain-home radar network formed the system foundation. These stations employed large fixed towers transmitting on frequencies between 20 and 55 MHz, corresponding to wavelengths of 13.5 to 5.5 meters. The long wavelength provided detection ranges exceeding 190 kilometers against bomber formations at altitude, but limited accuracy and prevented detection of low-altitude targets. Technical specifications. Transmitter power reached 350 kilowatts peak, 20 kilowatts average. The system employed separate transmitting and receiving towers, with receiving antennas arranged to provide directional bearing through phase comparison. Height finding relied on comparing signal strength from multiple antennas at different elevations, an imprecise method that contributed uncertainty to altitude estimates. Chain-home low stations complemented the primary system, employing rotating antennas operating at 200 MHz, 1.5 meter wavelength. These detected low-altitude aircraft but with reduced range, maximum approximately 50 kilometers. The combination provided overlapping coverage across approach corridors. The Observer Corps, consisting of approximately 30,000 civilian volunteers at 1,400 observation posts, visually tracked aircraft crossing the coast. Observers used height estimation instruments and reported aircraft type, number, heading, and altitude via telephone networks. While less precise than radar, the Observer Corps provided altitude data more accurately than chain-home and tracked aircraft over land where radar coverage proved incomplete. Information flowed to filter room at Fighter Command Headquarters, Bentley Priory. Staff officers assessed incoming reports, correlated multiple sightings of identical formations, filtered spurious contacts, and constructed the recognized air picture. This filtered information displayed on operations room plotting tables. Large map tables were personnel position markers representing formations. The system's hierarchical structure enabled efficient response. Fighter Command HQ maintained strategic overview. Group headquarters controlled fighter resources within geographical sectors. Sector stations, operational airfields with dedicated operations rooms, controlled individual squadrons. This structure permitted rapid response while preventing information overload at any organizational level. Combat effectiveness depended critically on system efficiency. Average time from initial radar detection to fighter interception: 15 to 20 minutes when system functioned optimally. This required fighters already airborne or at immediate readiness. The system enabled fighter command to maintain aircraft at various readiness states: airborne patrol, cockpit readiness, 2 minutes, readiness, 5 minutes, available, 30 minutes, and vector-specific squadrons against specific threats, maximizing force employment efficiency. 2.3 Campaign phases and operational analysis. The Battle of Britain progressed through distinct operational phases reflecting evolving German strategy and British response. Phase 1, July 10th to August 7th, 1940, Channel and coastal operations. Initial operations focused on channel convoys and coastal installations. Luftwaffe objectives: test British defenses, achieve local air superiority over the Channel, and attrit fighter command through combat. RAF objectives: defend shipping, prevent establishment of air superiority, and preserve fighter strength. Statistical analysis: Luftwaffe flew approximately 5,000 sorties during this period, losing approximately 180 aircraft. RAF lost approximately 70 fighters in combat, plus additional aircraft to accidents and ground attack. The loss ratio favored fighter command, while British fighter production exceeded losses. Convoy losses reached unsustainable levels, leading Britain to suspend daylight channel convoys, a tactical defeat but strategically acceptable given fighter command preservation. Phase 2, August 8th to September 6th, 1940, the critical period. Luftwaffe operations shifted to systematic attacks against RAF infrastructure, radar stations, forward airfields, sector stations, and aircraft production facilities. This represented doctrinally sound strategy for achieving air superiority: destroy fighter defenses at their source. August 13th, Adlertag, Eagle Day, marked intensified operations. Luftwaffe planners scheduled concentrated attacks to overwhelm defenses. Poor coordination and weather-degraded results, but established operational pattern. Multiple large raids daily against infrastructure targets. Damage assessment reveals effectiveness. Several forward airfields sustained heavy damage, though none became permanently non-operational. 6 chain home stations received damage, all restored within 24 hours except Ventnor, offline for 3 days. Most critically, several sector stations, Biggin Hill, Hornchurch, North Weald, Kinley, sustained repeated attacks degrading operational capacity. Fighter command faced critical stress during this phase. Pilot casualties: approximately 350 killed, seriously wounded, or missing during this 4-week period. Pilot training schools produced approximately 260 replacement pilots, a deficit of 90 pilots. Experienced squadron commanders and flight leaders suffered disproportionate casualties, degrading unit combat effectiveness. Several squadrons required withdrawal for rest and reconstitution. Operational sustainability calculations, conducted by doubting staff, projected that continuation of this attrition rate would reduce fighter command effectiveness below critical thresholds within approximately 2 weeks. The command approached potential operational defeat through cumulative attrition. Phase 3, September 7th to September 30th, 1940, the turn. On September 7th, Luftwaffe strategy shifted dramatically. Operations concentrated against London rather than airfield infrastructure. This decision derived from multiple factors: Hitler's order for retaliation following RAF raids on Berlin, belief that fighter command approached collapse and would commit all reserves to defend London, an assumption that destroying London would break British morale. From fighter command perspective, This shift provided critical operational relief. Sector stations received respite from continuous attack, enabling repair and restoration. The longer distances to London reduced Bf 109 combat time over target. Escort fighters required departure while bombers remained vulnerable during withdrawal. The concentrated nature of raids simplified interception planning. Fighter command could predict target and mass forces accordingly. September 15th, subsequently designated Battle of Britain Day, saw maximum effort by both sides. Luftwaffe dispatched 2 major raids, totaling approximately 1,500 aircraft. Fighter Command responded with maximum deployment, bringing No. 12 Group Squadron South to reinforce No. 11 Group. Large-scale air battles developed over southeast England. Contemporary claims reported 185 German aircraft destroyed, a vast overestimate reflecting multiple pilots claiming the same aircraft. Actual German losses: 56 aircraft, including 20 Bf 109s and 16 Bf 110s. RAF losses: 28 fighters with 13 pilots killed. While less dramatic than initial claims, these losses proved unsustainable for Luftwaffe bomber formations, particularly the heavily mauled Bf 110 destroyer units. 2.4 Assessment and Strategic Implications. Campaign outcome reflected multiple interacting factors beyond individual combat prowess. Analyzing these systematically illuminates why Fighter Command survived and Luftwaffe operations failed. Operational factors. Defensive advantage. Operations over home territory provided pilot recovery, aircraft salvage, and infrastructure support. System efficiency. Integrated air defense multiplied fighter effectiveness through optimized force employment. Production rates. Britain produced 1,900 fighters July-October versus 775 Bf 109 ES for Germany. Pilot training. RAF maintained training infrastructure throughout campaign. Luftwaffe diverted training resources to combat units. Strategic factors. German operational errors. Shift from airfield to city attacks at critical moment. Range limitations. Bf 109 combat radius restricted operations. Bf 110 proved vulnerable. Divided objectives. Simultaneous attacks on multiple target categories prevented concentration. Intelligence failures. German intelligence consistently underestimated fighter command strength. Technological factors. Radar advantage. Provided strategic warning, eliminating need for standing patrols. Radio communication. Enabled ground control and tactical coordination. Aircraft quality. Spitfire Hurricane combination proved adequate against Bf 109, Bf 110 force. Production capacity. British industry exceeded German fighter production despite bombing. The campaign established doctrinal precedents that shaped subsequent operations. It demonstrated that strategic bombing without fighter escort faced prohibitive losses. It proved that technological systems, radar, communications, integrated command and control, could multiply combat effectiveness beyond pure force ratios. Most significantly, it showed that air power alone, without complementary land and naval operations, could not compel national surrender against determined opposition with effective defenses. German failure to achieve air superiority prevented Operation Sea Lion. Without air cover, amphibious forces could not survive Royal Navy intervention. Britain survived the immediate invasion threat, maintaining the Western Front and providing base for eventual liberation of Western Europe. Part 3. Strategic Bombing, Theory and Reality. 3.1 Doctrinal Foundations and Pre-War Theory. Strategic bombing doctrine emerged from interwar theorists asserting that air power could independently win wars by destroying enemy industrial capacity and civilian morale. Italian theorist Giulio De Hette argued in The Command of the Air that bomber forces would always penetrate defenses, and that strategic bombing would force capitulation faster and with fewer casualties than ground campaigns. British Air Marshal Hugh Trenchard and American Brigadier General William Billy Mitchell advanced similar theories, arguing for independent air forces focused on strategic bombing. These doctrines shared common assumptions: that bombers possess sufficient speed, altitude, and defensive armament to survive interception, that navigators and bombardiers could accurately strike specific industrial targets, that destroying key industrial nodes would collapse enemy war production, and that civilian populations would demand peace when subjected to sustained bombing. The combined bomber offensive against Germany tested these assumptions under operational conditions, revealing substantial gaps between theory and reality. 3.2 RAF Bomber Command. From precision to area attack. RAF Bomber Command initiated operations in 1939 with daylight precision attacks against specific military and naval targets. Early operations against German naval forces demonstrated fundamental problems. On December 18, 1939, 24 Wellington bombers attacked German warships at Wilhelmshaven. Luftwaffe fighters intercepted the unescorted formation, destroying 12 aircraft, a 50% loss rate that could not be sustained. This catastrophic loss forced doctrinal revision. Bomber Command shifted to nighttime operations, accepting reduced accuracy in exchange for survival. However, night navigation proved far more difficult than anticipated. The Butt Report, analyzing 650 night raid photographs from June-July 1941, revealed that only one aircraft in 3 dropped bombs within 5 miles of target. Over the Ruhr, with industrial haze and heavy flak, only 1 in 10 aircraft struck within 5 miles. These findings forced further adaptation. If crews could not locate specific factories, they could navigate to large urban areas and attack city centers. This became official policy under Air Marshal Arthur Harris, appointed Commander-in-Chief Bomber Command in February 1942. Area bombing doctrine rationalized attacks on urban areas as strikes against industrial workers, transportation infrastructure, and general war-making capacity. Operational implementation required technological development. The GE radio navigation system, operational from March 1942, used time difference measurements from synchronized ground transmitters to provide position fixes accurate to within a few miles, sufficient for navigation, but not precision bombing. H-2S ground mapping radar, introduced in 1943, provided crude imagery of terrain features, enabling target identification through cloud. Tactical innovation improved effectiveness. The Pathfinder Force, established August 1942, marked targets with incendiary markers for following bomber streams. The bomber stream tactic concentrated aircraft in time and space, saturating German defenses and reducing individual aircraft exposure. Introduction of window, aluminum strips cut to radar wavelengths, degraded German radar-directed defenses, dramatically reducing loss rates during July 1943. Major operations demonstrated both capability and limitations. The 1,000-bomber raid on Cologne, May 30th to 31st, 1942, involving 1,047 aircraft, destroyed approximately 13,000 buildings and killed 469 people. Significant destruction, but far short of decisive effect. The Hamburg raids, July-August 1943, created firestorms killing approximately 42,000 people and destroying 16,000 buildings. Dresden, February 13th to 15th, 1945, killed approximately 25,000 and destroyed city center. These operations inflicted massive destruction, but did not force capitulation or collapse war production. 3.3 U.S. 8th Air Force. Precision Doctrine Under Fire. The United States Army Air Forces approached strategic bombing with different doctrine. American planners believed that heavily armed four-engine bombers, B-17 Flying Fortress and B-24 Liberator, could fight through defenses to conduct daylight precision attacks. The Norden bomb sight, capable of theoretical accuracy measured in tens of feet, would enable destruction of specific industrial bottlenecks. Technical specifications of primary aircraft. The B-17G mounted 13.50 caliber machine guns in powered turrets and handheld positions, providing defensive coverage across all approach angles. Maximum bomb load reached 8,000 pounds for short-range missions, typically reduced to 4,500 pounds for deep penetration rates. Service ceiling of 35,000 feet and maximum speed of 287 miles per hour provided altitude and speed advantages over early war German fighters. Initial operations appeared to validate doctrine. Early raids against French targets encountered moderate opposition and achieved acceptable accuracy. However, deep penetration raids into Germany revealed severe problems. The August 17, 1943 Schweinfurt-Regensburg mission targeted ball bearing production and aircraft factories. Of 376 bombers dispatched, 60 failed to return, 16% losses. Many returning aircraft sustained heavy damage. This loss rate exceeded sustainability thresholds. German defenses evolved specifically to counter daylight bombing. Fighter tactics developed to exploit bomber vulnerabilities. Head-on attacks, while difficult to execute, targeted the bomber's least defended forward sector. Concentrated attacks on individual bombers, rather than dispersed attacks across formations, achieved better results. Specialized weapons included 21 cm rockets and 30 mm cannon firing large high-explosive projectiles capable of catastrophic damage. The second Schweinfurt raid, October 14, 1943, culminated the crisis. Deep penetration without fighter escort faced massed German interceptors. Of 291 bombers attacking, 77 were shot down and 121 sustained damage, combined losses of 68%. This Black Thursday demonstrated conclusively that unescorted daylight bombing could not continue. The solution emerged through escort fighter development. The North American P-51 Mustang, originally designed to British specifications, received transformation through Packard-manufactured Merlin engines. The resulting aircraft combined long range with performance matching German fighters. With external drop tanks, P-51s could escort bombers throughout Germany. Introduction of P-51s in quantity during early 1944 transformed the campaign. German fighters now engage American escorts throughout their operational radius. Bomber losses declined while German fighter losses mounted. The Luftwaffe faced attrition warfare against superior numbers with dwindling pilot training quality. By April 1944, German fighter arm approached collapse, granting Allies air superiority over Western Europe, essential for successful invasion. 3.4 Strategic Effects and Effectiveness Assessment. Evaluating strategic bombing effectiveness requires examining multiple dimensions: physical destruction, economic impact, resource diversion, and psychological effects. Physical destruction. The campaign destroyed approximately 3.6 million dwelling units, displacing 7.5 million Germans. Major industrial cities sustained destruction of 50 to 70% of built structures. Transportation networks faced systematic disruption, with attacks on rail yards, bridges, and waterways degrading logistics. The synthetic fuel campaign, beginning May 1944, reduced aviation gasoline production by 90% by war's end. Economic impact. German industrial production increased throughout 1943 and into mid-1944 despite intensifying bombing. Albert Speer's rationalization of war production, dispersal of facilities, repair organization, and labor mobilization maintained output. Only during late 1944, as oil production collapsed and transportation networks failed, did production decline catastrophically. The United States Strategic Bombing Survey concluded that strategic bombing reduced German production by approximately 15% until mid-1944, increasing to decisive levels only in final months. Resource diversion. Germany allocated approximately 1 million personnel to air defense, including 900,000 in flak batteries and 140,000 in fighter units. Industrial resources produced 40,000 anti-aircraft guns, 10,000 of 88 mm heavy caliber, and 55,000 fighters. These resources, devoted to defense, could not support ground forces. The survey estimated this diversion equivalent to 20% of German military production. Civilian casualties. Approximately 400,000 German civilians died from bombing, with additional 800,000 wounded. These casualties concentrated in urban areas, affecting industrial workers and their families. However, civilian morale did not collapse. Nazi control mechanisms prevented political disaffection from translating into resistance. Production workers continued reporting despite housing loss and personal trauma. Strategic assessment. Strategic bombing did not independently win the war, contradicting pre-war doctrine. However, it contributed significantly to Allied victory through multiple mechanisms: resource diversion from ground forces, destruction of fuel production enabling ground force mobility, disruption of transportation preventing strategic movement, attrition of Luftwaffe fighter forces granting tactical air superiority, and forcing Germany to fight multi-front war, including defense of homeland. The campaign demonstrated that modern industrial states with totalitarian control could sustain production and morale despite massive destruction. Decisive effect required systematic destruction of specific industries, particularly fuel, rather than general area bombing. Air superiority proved essential for strategic bombing success, requiring long-range escort fighters, a capability not available until 1944. 3.5 Human cost and operational experience. The bomber offensive produced casualty rates comparable to major ground campaigns. RAF Bomber Command flew 364,514 sorties, dropping 955,044 tons of bombs. Personnel statistics: 125,000 aircrew served, 55,573 killed in action, 44.4%, 8,403 wounded, 9,838 prisoners of war. The probability of completing a standard tour of 30 operations without death, injury, or capture approximated 25% during the most intense periods. American Act Air Force flew 299,950 combats sortis, dropping 695,000 tons. Personnel casualties: 47,000 casualties, including 26,000 killed. Loss rates varied by period, with unescorted operations producing 5 to 10% losses per mission versus 1 to 3% after escort fighters arrived. Operational conditions were physically brutal. Bombing missions occurred at altitudes of 20,000 to 30,000 feet, where ambient temperature reached -40 to -50 degrees Celsius. Oxygen systems prevented hypoxia but could not address cold. Electrically heated suits provided limited protection. Frostbite casualties were common. At these altitudes, even minor aircraft damage could prove catastrophic. Broken windows or fuselage holes admitted -50-degree airflow at 200+ miles per hour. Defensive fire created an environment of random sudden death. German 88 mm flak shells burst at set altitudes, creating shrapnel spheres 60 feet in diameter. A single shell fragment could destroy hydraulics, fuel tanks, or control surfaces, or kill crew members instantly. Formations flew through flak fields where hundreds of shells burst simultaneously. Pilots could not evade. Evasive maneuvers would break formation integrity, increasing vulnerability to fighters. Fighter attacks produced catastrophic damage within seconds. A 2-second burst from 30mm cannon could tear off wings or detonate fuel tanks. Damaged bombers faced agonizing decisions: remain with crippled aircraft possibly reaching friendly territory, or bail out over hostile territory facing capture or death. Many aircraft sustained damage, leaving crew unable to bail out, forcing them to ride aircraft to ground impact. The psychological burden proved immense. Crews knew mission dates in advance, producing anticipatory stress. Loss rates meant crews regularly witnessed squadron mates' aircraft explode, burn, or plummet. The requirement to continue flying despite accumulated trauma produced combat exhaustion, now termed PTSD, at rates approaching 20 to 25% among long-service personnel.